Welcome back to Basics again. In this video, we will be looking at the basics of a current-carrying conductor and the magnetic field around it. A current-carrying conductor creates a magnetic field around it. In this picture, the direction of the current is determined by the poles of the battery. The long line of the battery is positive and short line is negative. Remember to follow conventional current. The charge moves from the positive pole through the circuit to the negative pole of the battery. The magnetic field around the straight wire can be shown using iron filings, just like the other magnetic fields around permanent magnets. The iron filings form circles around the wires. The direction of the magnetic field can be determined using the right-hand rule. Something to note is that the current and magnetic field are perpendicular to each other. Let's explain this further. Right-hand rule states that you must grasp the wire with the right hand so that the thumb points in the direction of the conventional current. Then, the wrapped fingers will encircle the wire in the direction of the magnetic field. The magnetic field is stronger in the area around the wire and weakens as the circles get further away. The larger the current, the stronger the magnetic field is. If the current is coming out of the page, it is represented by a dot. If the current is going into the page, it is represented by a cross. An easy way to get your right hand in the correct direction is to make the thumbs up sign with your right hand. If you look at your thumb from the top of your hand, you see a single point. If you look at the bottom of your right hand, there is actually a little cross. If we have a single loop of wire, the field around the loop can be determined using the right-hand rule. The current comes out of the page on the left, so your thumb points up and your fingers curl anti-clockwise, while your thumb will point down into the page and your fingers will curl clockwise on the right. It is important that you practice this with your hand and see if you understand. Looking at the magnetic field is in the same direction in the middle at M. Many turns of insulated wire are called a solenoid. Looking at many turns of wire, the pattern seen for one coil is repeated for each coil. As you can see in the diagram, the current comes out at the top, shown by the dots, and goes in at the bottom, shown by the crosses. The field lines point in the same direction in the center of the solenoid. Current in solenoid produces a stronger magnetic field inside the solenoid than outside. The field lines in this region are parallel and closely spaced, showing the field is stronger there. Field lines outside the solenoid are similar to that of a bar magnet, and it behaves in a similar way. We can see that the field still goes from north to south. Strength of magnetic field can be increased by increasing the current in the coil, increasing the number of coils in the solenoid, and using a soft iron core within the solenoid. The right-hand rule can be used to find the direction of the magnetic field of a solenoid. To do this, you should point the wrapped fingers along the coil in the direction of the conventional current. Then the thumb will point to the direction of magnetic field within the solenoid. That is, the thumb then points in the direction of the North Pole. This is very useful for using Lenz's law later on.